There you go. Okay. The lab or the research group is called the Climate Coastal Ecosystem Laboratory, and I'll be honest about this. The reason it's called that is because when you apply for CFI money, you need to give your lab a name. And I didn't realize that it was like the last day I was submitting the thing, I had a name on it. And so that sort of has become our name. The research, a lot of it falls under this title, a lot of it doesn't. But we sort of call ourselves that. There's a plaque on the door that the students' offices are in. And so you're going to, a lot of you know each other already, but you're going to meet and hear from Shinru Lee, and then Pedro Gonzalez, Heather Summers, Sarah Cannon, Katrina Bernos, who's going to speak briefly. Katrina's an undergrad that just started working with us, and Seth Wines. And they're all going to just sort of go over and talk about their research. And I thought just at the beginning I'd give you a sense of where I'm coming from and how we have a kind of diverse set of things going on in the group. And I would just say what's happening in the research group right now is representative of a good chunk of what I've been doing over the years, but there are things that sort of fall out far outside of the bounds, and it's just as students come and go, things change. Best way to put this is, so I call myself a climate scientist. There's no, badge or brand you get at any point, so I don't know what technically makes somebody a climate scientist, but I did a PhD in atmospheric and oceanic sciences, and that's usually like the degree people do if they want to be a meteorologist or a climatologist. But the only difference was that my advisor he was one as well. He had the same degree I did. But he was really working on like interactions between climate and like the planet and like the surface of the planet, literally like the interactions of carbon and heat and stuff. And so I was really, the reason I worked with him is I was interested in learning all the physics of the climate system, but then using it to understand the climate impacts on other things. And so my work sort of diverges around that. And really what I'm interested in sort of why the climate matters. So why does it matter if the climate changes, it varies from year to year? And so some of this work then borders on ecology, borders on marine biology, sometimes it's social sciences, etc. And it's just because I'm trying to answer the same sort of set of questions constantly. So the four main things that have been going on, you'll hear about some of it today, that I've been interested in over the past few years is the first is just how are ocean temperatures and sea level changing across the Pacific. So as as climate is changing, and so I've had students, nobody's really working on this now, but we've had people in the group in the past working on El Nino events and how El Nino events have changed over time. So that's really like more climate physics sort of in a way. That's one thing. And the sea level work is related, you're going to hear a little bit about this, related to some work we've been doing in the Central Equatorial Pacific. The second question would be what has been the majority of the scientific research I've done in the past few years is going on how climate change is affecting coral reefs and how they can adapt over time. So one of the things that I was contributing personally the past few years was working with a group of students to build a database of all the reports of coral bleaching have happened around the world in the past. And so this is sort of just to give you a sense, like, so we've gone through and just trudged through the literature, contacted people around the world to count up how many bleaching events were every year and did mapping of all of them. And so this is just sort of per year observations in the database. And I realized I don't have the 2014 through 2017 data in here yet, but I just received the final file like Friday. So this is some of the work we're doing modeling of future projections for coral reefs, and you'll hear a little bit about that today as well. The third thing you won't hear about so much, but there's been a lot of my own personal work in the past 10 years is trying to figure out how we can help the developing world adapt to climate change. So one is in the islands of the Pacific where I work, looking specifically at the challenges they face. This is a seawall that was built and built poorly in Tarawa, the capital republic of Kiribati, which you'll hear about. So some of it is like the science of this, some of this is the social sciences, and so I ended up with Melinda Kaler, who's here in IRES, looking at like where the money comes from. And we've done research on like what fraction of money goes to adaptation and things like that. And then really the last question, which Jordan alluded to, is really sort of how can scientists effectively engage with the public about climate change. And some of this is actually research, and you'll hear what Seth's working on a little bit. Some of it is just the outreach and engagement activities, and I would say that if I had to break my time up as to what I spend my time on, it's probably about a third of like my professional life is spent doing things related to this. And it can be rewarding, it can be exhausting, and I feel like I've learned a lot from the process. I get a lot of nasty emails. This is one of my favorites because I don't like, he misspelled shyster. So I don't know if he was being, the person was being anti-Semitic. I like my slight misspelled, it probably was. And then the occasional, this is weirdly common. I've had this several times. Vengeance is mine, I will repay. I don't know if I should be worried about those emails. Anyways, so that's sort of the suite of things I've been interested in over the years, and it's led to this smart group of people being in the lab, and we found projects that sort of meld what they came interested in and what I was interested in. We sort of found the sweet spot between them. So we'll get started I'll introduce Shinru Liu, who's been in the lab now for, she's in the second year of her PhD. She did a master's degree at Simon Fraser University with Kirsten Ziegfeld in climate science work, and came here to work on ocean temperature issues.
So, hello everyone, my name is Shinru Liu. So as Sam said, my research interests focus on sea surface warming and marine heat waves. So as we know, the Earth has warmed unprecedentedly over the past century due to the human activities such as fossil fuel burning, land use change. So the ocean warming dominates this increase in the energy stored in the Earth's system due to its large heat capacity. So indeed, ocean really plays an important role on the climate change because it's huge heat reservoir and carbon reservoir. So that's why we care about the ocean. While the whole ocean warming is a slow process due to its large specific heat of the water, the slow ocean overturning circulation, and the huge ocean volumes, the sea surface warms fast due to the rapid interactions with the atmosphere, and thereby the impacts of the sea surface warming is more imminent. Especially the periods of the anomalously warm events, marine heat waves, is really significantly affecting the marine ecosystems around the world. So there's a growing body of research on ocean warming, really focused on the mean trends of sea surface temperature and some heat stress matrix, such as the accumulative heat stress. Well, despite these important advances, there's a limited research into the observed and predicted changes in the structure of the sea surface warming. So it's like we can zoom in this warming trend of the surface to see the to evaluate the fine-scale dynamics of these variances of the sea surface temperatures. So, for example, say along with the sea surface warming, does the sea surface temperature anomalies with the higher peak, like the curve A, or with the longer duration of the curve B, become dominant in contribution to the rising sea surface temperature trends. So based on this knowledge gap, we are interested in two research questions. So first is, what are the changes in the structure of the rising sea surface temperatures over the past 4 decades? And the second is, how well global climate models output can capture the observed changes in the structure of the sea surface warming. So for answering these two questions, we propose to decompose the observed and the global climate models, simulated trends in the mean SST and the cumulative heat stress. The emergence of the high-resolution daily satellite-derived sea surface temperature can make it accessible to do this kind of research. Such as we can compute the rate of the changes in the number of days that exceed a warming trend of a year over the past decades. And we can also compute the rate of changes in the heat peak of the year over the past decades, and use this analysis on the observed changes in the structure of the sea surface temperatures in contrast to the global climate model simulation outputs. So we think this research is important because it can help us to understand the structure of sea surface temperature changes and the extremely high sea surface temperature warm events, marine heat waves, and thereby can facilitate our understanding on the marine ecosystems, for example, coral reefs, in different locations to respond to these thermal stress. And despite the ocean warming impacts on the marine ecosystem, like coral reefs, the impacts of light, solar radiation may also be key to the marine ecosystem coral reefs. So these things will be discussed by Pedro. So, yeah.
Hi everyone. My name is Pedro Gonzalez. Maybe you know I am the one in charge of the coffee Monday and Friday. But today I'm going to talk about my research and what I'm doing actually in the lab. So keywords that you have to remember through the presentation is coral bleaching, sea surface temperature, solar radiation, and modeling. So the general idea of my research and also coral bleaching. You know that corals are animals and plants living together, zooxanthellae, microalgae living together. They're living in this close relationship, in this symbiosis, and it is known that solar radiation and sea surface temperature are inextricably linked to bleaching response. So any change in these variables or in any other variable is so important for them because they can disrupt this relationship. If you read about coral bleaching, maybe you will notice that they talk about sea surface temperature. They also say that response to solar radiation, there is several studies that talk about solar radiation, light. They mention that light is so important, but it is interesting that there is not taken into account in any methodology. So if you are analyzing coral bleaching, you take just sea surface temperature for one reason, because sea surface temperature gives you the most information, which is true, is really accurate. Is by the way, for example, is used by Coral Reef Watch from NOAA. So they use models of sea surface temperature only, which is really accurate. But they mentioned that solar radiation is important. They are already making some studies trying to integrate solar radiation. There are some products that are on develop, but they are not integrating so far. So how important is light for coral bleaching? You will read that it's extremely important. Even that is the triggering, or having proposed that is the triggering, not the temperature, but the solar radiation is the triggering of coral bleaching. So I am interested in analyze both relationships, doing models, and see if I can integrate sea surface temperature and light in a single algorithm. So both together, working together, see if I can do it. So just briefly, seasonal photosynthetic response. This is how it's supposed to be responsive, or how it's responsive, by the way, the corals. So corals and any other organism is always, the living organism, we are always acclimating. We are always making adjustment to the environment, right? So as corals do in the environment, so they have to have a seasonal acclimation. They have seasonal acclimation, so they have this plasticity. That is, if this plasticity is at some point is disturbed, they are going to get bleached. So, for example, here's the summer and winter adaptive corals. So the first thing that we will see is that the efficiency is completely different. I'm talking about photosynthesis of the zooxanthellae. So they are really, really efficient during winter, and they are not efficient, but they have a maximum photosynthetic rate in summer. So any anomaly is going to disrupt this relationship. So there are some proposals that the coral bleaching and light is even, for example, light and sea surface temperature, they act in a synergetical way or in an additional way, where I have seen or I have heard some proposals that they are even antagonists. So the light is even enhancing the stability of corals. This is the first chapter. So I am analyzing low temperature and solar radiation. I have seen that sea surface temperature and light radiation are significant. So I am running a model, I already ran it. I found that they are significant through logistic regression. And this is important because if we think cold coral bleaching, it's like we always hear like high temperature is going to trigger coral bleaching, not cold temperature. So here it's important because they will have shorter time for recovery. So they will have shorter time for acclimation as well. So I say corals are cool, corals are radiant, but in terms of thermal bleaching, they cannot be together. So cold temperature and high radiation is not working for them. Warm temperature, would be the second chapter of my research, is warm temperature, solar radiation, and the effect of cloudiness. So in this part, I will analyze if there is any correlation among photosynthetic available radiation and cloudiness. So if you think the light that is reaching the ocean and the light that is reaching the corals, I want to see if there is any correlation among with cloudiness. They have seen that some cloudiness in the sea can even shield corals and protect corals against coral bleaching. So this is interesting because I'm interested in see what fraction of the sky is cloudy. If I can see a pattern, some places are more cloudy or are prone to be cloudy, so they can be shielded because there are some researchers that say like cloudiness can shield coral from bleaching. So that's the question regarding of this chapter. If there is any relationship among coral bleaching and cloud cover. So that's the main point of this chapter. So again, also I want to do it in a parsimonious methodology. There are several attempts. You can find methods of 13 different variables, but I think that they are overfitting, so I'm trying to do it in the most parsimonious way, just 2 variables or something like that, and if they give me enough information. Finally, the projection of coral bleaching. So with the outputs of the previous research, I will run it with different scenarios, knowing if they are responding correctly, sea surface temperature and light, and then see the different scenarios. If I know that temperature is going to be higher, how it's going to change cloud cover, for example. If there is a relationship with cloud cover and photosynthetic available radiation, then I can construct different scenarios. I will know, or I can extrapolate the implication that they could have. And my aim in this part is try to find if there is I can say there is a potential refuge of corals for different scenarios of climate change. And this will be helpful for local stressor assessment. So there are many research on local stressor assessment, that nutrients inputs also are affecting this part. Population growing, etc., overfishing, all of them can help, the outputs here can help this part. And yeah, that will be all.
Great, so my name is Heather, and I am going to kind of talk a little bit more, kind of build off of what Shinru and Pedro have talked about already. So as I mentioned, with the rising sea surface temperatures, corals are under stress, and that leads to coral bleaching. So here we have a map that shows the ratio between the interannual range in maximum sea surface temperatures and the seasonal range in monthly sea surface temperatures. So with most corals around the world, they have a value less than 1. So that means that they have high seasonality, they experience high seasonality and low to moderate kind of variability in their sea surface temperatures each year. Now the interannual range for Kiribati, which is the area highlighted here with the black circle, the interannual range exceeds the seasonal range by 2 to 6 times. And so pretty much that means that the sea surface temperatures in Kiribati vary more from year to year than they do seasonally. Now, this temperature variability is quite unique, and it only occurs in coral reef regions within 2 to 3 degrees of the equator. So previous work done in the lab has found that frequent temperature variability makes corals more resistant to heat stress. So corals in Kiribati have this unique bleaching resistance, and the highest bleaching resistance was found in the most disturbed reefs with the lowest species biodiversity and structural complexity. And I'm going to focus particularly on the structural complexity. So the problem arises when you have supposedly healthy reefs being associated with having a low structural complexity. And that's because the structural complexity, it's the three-dimensional structure of a reef, and it provides frictional resistance as waves and currents pass over the reef, thereby protecting the shorelines. So shoreline protection in Kiribati is particularly important since the country is comprised of islands where most of the land is less than 2 meters above the mean sea level.
So you're saying they're more likely to bleach in highly disturbed reefs?
Yeah, yeah. So this kind of raises an interesting, so this raises an interesting question about whether the reefs that are most resistant to bleaching, whether they kind of will provide the shoreline protection necessary. So that's kind of leading into my project, which is looking at the trade-off between reefs that are resilient to disturbance and those that offer shoreline protection. So data collection was predominantly carried out by SCUBA, and that was done with Sarah and Simon, and that was done at 16 outer reef sites in Kiribati's Tarawa and Abayang atolls, and that was done during mid-April to early May of this year. So in order to look specifically at the coral biodiversity, we took quadrat photos every 50 centimeters along the 50-meter transect, and then we analyzed that in coral point count, and we identified in particular the corals to the genus level, with the exception of Parietes reefs, and I'll kind of mention that a little bit more later. And then to analyze the structural complexity, I took overlapping high-resolution underwater images over a 10 by 10 meter grid, and that was using this lawnmower pattern, which you can kind of see right here. Now, the reason for this lawnmower pattern is I want to be able to get at least an 80% overlap within each of the photos, so that when I line them, they stitch together well. So there's about 1,500 to 3,000 individual images per site, and then they were lined using Photoscan, and then this is the models that you get at the end. So this is just a screenshot, and it's like a full 3D. What I'm hoping to do now is quantify the structural complexity using the digital elevation models that are output through these 3D models here. So looking at the data that we have so far, so here we have a stack bar graph with the sites on the x-axis and the benthic cover the percent benthic cover on the y-axis. So sites in North Tarawa and Abayang right here, they show high biodiversity of reef-building corals. In contrast, right here, 7 of the 8 sites in South Tarawa are dominated by Parietes reefs. So that's shown here in the purple. And that is a reedy resilient coral that has a generally low geometric complexity in comparison to other major reef-building corals. Now, the major driver of this kind of difference in coral community composition is likely to be the human population. And that's because, so this here, the area outlined in red is South Tarawa, and the outer reefs in this area have high pollution and sediment loading, and that's due to the growing urban population. So there's about 50,000 people that live just within that area, so that's about 3,000 people per square kilometer, so that's about equivalent to, population density equivalent to about Seattle, except you don't have skyscrapers or anything like that. Most homes are only about 1 story, at the very most, usually 2. And then there's also shoreline modification, which I'll talk about just in a second. And all of these are kind of influencing the coral reefs in this area, and that's why we're having only Parietes reefs being able to thrive. So there are site-specific differences in the reef-building corals, and hence the complexity. And this is consistent with data from past years. Now, in order to get more of an idea of the wave energy that's reaching the shorelines, I looked at the width, water depth, and surface roughness of the reef flats. We were able to do shoreline measurements at all 8 South Tarawa sites, and then just due to logistics, we could only do measurements at 1 North Tarawa site. Now, a wide reef flat with a high water depth is going to be able to dissipate more wave energy compared to a narrow reef flat with a high water depth. Now, preliminary analysis of the width and water depth of the reef flats is showing that there's no consistent large differences between these sites in South Tarawa and the site in North Tarawa. Now, I also mentioned that the surface roughness also plays a really big role, and that's because reef flats that have a smooth rock or algal turf, such as the ones in South Tarawa, are going to dissipate less wave energy compared to reef flats that have small boulders, such as the ones in North Tarawa. And a lot of the boulders in South Tarawa, they used to be there, but they were removed for building infrastructure such as homes and seawalls. So Simon kind of showed an image at the beginning of a seawall. So, and this all is negatively affecting the natural coastal processes that protect these shorelines. So it's mainly human activities that have impacted the surface roughness of the reef flats, and hence the shoreline protection. So I'm now going to pass it off to Sarah to talk about her work in the Marshall Islands and Kiribati.
Thank you. All right, so like Heather was talking about, Kiribati is pretty special because of the sea surface temperature variability that happens there every year. And I also did my master's. I'm a second-year PhD student in Simon's lab, but I've done my master's with him as well. And for my master's, I worked in the Marshall Islands, which is just north here. So just north of Kiribati, a little bit further north of the equator. So it doesn't have the same sea surface temperature variability that Kiribati has. And I'm interested in looking at how the local impacts of population intersect with the impacts of climate change in these places. And so we kind of have a natural experiment set up here between the Marshall Islands and Kiribati, because we have these two atolls that are right next to each other in the Marshall Islands, Madro and Arno. And Madro has a big population of about 30,000 people, whereas Arno has a population of less than 2,000. And then in the Gilbert Islands in Kiribati, we have the same situation where Tarawa has a population of, I think, around 50 to 60,000 people, whereas Abayang has less than 1,000. So it's a nice natural experiment here where we can kind of compare across a grid of sea surface temperature variability and human disturbance to see how the reefs are different among those places. And so we do that by doing bed-day surveys, but a few other ways as well that I'll talk about. So I'm still in the planning processes of my PhD. I'm still kind of trying to figure out exactly how we're going to go about this, but here's some of the main questions that I'm thinking about. Mainly how past temperature variability impacts resilience to or recovery from bleaching events, which Heather talked about a little bit. We think that Kiribati, in places like Kiribati, where there's a lot more temperature variability, the reefs will be more resistant. But then also how local human disturbance plays into that as well. So again, we do look at this through a few different methods. We use benthic surveys, in which we look at community composition of coral and macroalgae to the genus level. We used, this was a new method, pulse amplitude modulation measurement, so PAM fluorometer, where we actually went down and took samples of the corals, brought them back. And then what that does is it measures the photosynthetic rates of the corals themselves, so we can get an idea of productivity across sites. We've only tried that in Kiribati, and I haven't had a chance to look at the data yet, so once we have an idea if those data are actually telling us something, we'll see if it's worth trying that again in the Marshall Islands, and then we can compare productivity across sites, across that grid that I showed you. And then we're comparing all of this across a gradient of human influence, which we quantify using the Normalized Difference Vegetation Index, which is something that we can get from satellites, where we look at how much green there is on land. And Katrina's going to talk about that, how we actually do that in a few minutes. But the reason why we use that instead of more traditional methods like population or distance from a population center or distance from a fish market, because a lot of places in Kiribati and the Marshall Islands are considered, we would consider highly disturbed, but they're not necessarily close to where people live. For example, in the Marshall Islands, there was a huge project to expand the airport there, and the human population there is very low. There was a ton of sedimentation that was smothering the reefs there. We saw the reefs there looked highly degraded. But if we used a kind of more classic method of human influence to quantify that there, it would have shown that we would have expected those sites to be healthy. so they're farther away from people. Okay, so that's one aspect. I'm also interested in looking at the more social, looking at the social side of conservation across Micronesia. I've been fortunate to work in various places across Micronesia. I worked in Yap in the Federated States of Micronesia as an undergrad, and then for my master's work I was in the Republic of the Marshall Islands, and now I'm working in Kiribati as well. And it's really interesting how different the approaches to conservation are in these various places. So Yap and the Republic of the Marshall Islands, well, the entire Federated States of Micronesia, they're part of the U.S. Compact Agreement, which means that they get money from the U.S. and their economy is very dependent on this money because they were occupied during World War II. The Republic of Kiribati is independent, has been independent from England since I think 1972 or something like that. But in Yap, the local constitution actually defends traditional management, so they have a right for things to be managed traditionally through the traditional management plans used by their communities. The Republic of the Marshall Islands is interesting because they have a thing called the Raymond Lock Plan, which is a Western conservation framework, but it attempts to integrate traditional management, but it's still, there's a lot of steps that are very bureaucratic, and it takes a very long time. So in places where they institute a marine protected area, for example, it could take up to 5 years of community meetings and kind of going through these very established steps. Whereas in Yap, a chief can literally just say, our community has decided that we want to protect this area, we're not going to fish there anymore. And then in the Republic of Kiribati, again, they're independent, but they don't have a lot of local resources, so they depend more on outside funding. For example, they get a lot of grants from Australia, and they still have a British system of parliament that they use. And so I'm interested in kind of comparing across these approaches and seeing what the relationship is between local autonomy and financial resources in effectively managing the marine resources in these places. And my guess is, this is just completely anecdotally, I'm assuming that places that have even less financial resources like Yap might still be able to manage things more effectively because they have so much local autonomy and they can decide to do things on their own. And then finally, this is kind of building off of my master's work, I've been looking at different ways to kind of quantify what a healthy reef is. And so this is something that scientists still don't really agree on. So you'll hear people talking about reefs being healthy, but that doesn't necessarily mean, but it depends on what aspects of health we're talking about. So sometimes that means that there's more coral cover, like there's a lot of healthy coral. Sometimes it means that there's less macroalgae, or it could mean structural complexity, like Heather was talking about. But if you polled everybody in this room and asked what a healthy reef was, you'd get different answers from everybody. And so often, conventionally, scientists will use macroalgae, or percent cover of macroalgae, as a way to say what a healthy reef looks like. And the idea is that at a site where there's a lot of algae, it's assumed that the reef is less healthy. But what we found is that many disturbed sites have low macroalgae cover and vice versa. So a lot of our disturbed sites had pretty much, I forget exactly what the percent was, but a lot high cover of like cyanobacteria or high cover of sponges. They had low macroalgae, but also low coral cover. And some of them even had high coral cover, like the ones that Heather showed that had a lot of Porites rufus, which is a weedy coral. So in 2016, John Bruno did a big meta-analysis of sites in the Pacific, where he compared macroalgae cover as a proxy for healthy reefs to human population, and he found no relationship between human population in the Pacific and macroalgae cover. And so he used that to say that human population is not influencing reef health in the Pacific Islands as much as we expect it to be, and instead we should be more worried about climate change than local impacts. And my guess is that it's probably a combination. I think it's more a combination of those things. It's not one or the other. And what we found in the Marshall Islands is that we use macroalgae genera instead of just using macroalgae as one whole class, that we actually find different relationships. So this is Arno on the left here, which is the less disturbed sites, and Madro on the right, which are the more disturbed sites. And you don't really need to look at the different types of macroalgae here, but what you can see is that sites in Arno, in general, all had macroalgae cover, whereas sites in Madro had a lot less in general. And we did find a statistical relationship between disturbance, the NDVI, and percent macroalgae cover for some of these different types of macroalgae cover here. And so again, I think with the Bruno study, when they used macroalgae as an entire category instead of separating things into genera, they might have actually masked the human influence that you would see in these sites. And we would actually assume, using that proxy, that some of these sites in Madro are healthy, when in fact we saw that they're really highly disturbed. And so we're thinking of redoing that meta-analysis that John Bruno did as part of my PhD, where we go back and hopefully break things down into macroalgae genera depending on what data are available. And so we'd be looking at the resources that he used as well as some of the resources that I used. And Katrina has been working on that. Katrina is an undergrad who just started working in our lab, and so she's going to talk a little bit about the work that she's been doing.
We're in this lab, and right now I'm mostly helping Sarah with her work. I'll probably be all over the place this year. So right now I'm working on that meta-analysis, basically just looking through the literature for where studies actually use the genus level data instead of just macroalgae, and looking at more areas in the Pacific. And then I'm also working on calculating NDVI for the different sites in Kiribati. So basically, as Sarah mentioned, NDVI is the normalized differential vegetation index, basically a relative measure of biomass, and we will be using it to see where there is human disturbance. So dense vegetation will have a very high NDVI, and we're comparing red radiance and we're comparing red radiance and infrared reflectance to get this calculation for NDVI, which we're able to calculate in GIS to map it on our map here. And so then we're able to see those calculations and get an average for our sites. I'll hand it over to Seth.
Yeah, so hi everyone, my name is Seth. I'm studying climate change mitigation with Simon, and I'm in my third year of my PhD. So during my graduate research, I looked at how individuals could best tackle climate change and sort of ranked different actions that they could take from low to high impact. And I found that educators and governments weren't really focusing on high impact actions, and were instead communicating a lot more about more in the moderate or low range. And so having done that research, I started my PhD, and I'm building off of that in a few different ways. So I have three sort of research questions that will hopefully end up being chapters in my thesis. One of them is, can members of the public make carbon trade-offs in their everyday actions? So if you think about, let's say, dieting, for example, if someone wanted to lose weight, they could probably make decent trade-offs going, oh, you know, I had 2 slices of pizza for lunch, that's a little bit more than usual, I'm going to hit the gym after this. And we'd expect them to be able to do that kind of budgeting. Can they do carbon budgeting, though? We'll find out. I'm also interested in the practices and beliefs of academics regarding air travel, which was one of those high-impact areas that we looked at before, and the political sphere as well. So going through them one by one, I just have an example of a question that I've posed to members of the public and undergrads as well. And so if the angle's not good, I'll just read it out for you. Someone takes a trip that requires driving 100 miles. If they switch from a standard mid-sized car to a mid-sized hybrid car, how far could they drive while still producing the same amount of greenhouse gases? Any guesses from the audience?
Is it a highway trip or is it a city trip? that matters for hybrid.
That's fantastic. You're too smart.
Okay.
Tone it down, bring it down here.
All right. 160.
Fantastic guess. Yeah, so this one, 150 is a really good guess. Anywhere between 115 and 190 is reasonable. That's like, yeah, that could happen in reality. Turns out this is one question that people are pretty good at answering. Some of the other questions, not so much. So that's carbon trade-offs. Air travel is a very inefficient way of moving around, and that's part of why it can be so bad for the climate. So I've just got a graph here showing, for instance, how much CO2 is produced when you move 1 ton of material 1 kilometer in a plane, and you can see that boats and trains are far more efficient ways to travel. So every flight that you take results in a lot of CO2 emissions. But it's not just CO2 emissions, there are also other greenhouse gases, and because they're released high in the atmosphere. They react with a lot of other chemicals up there and create additional warming, more so than if they were released on ground level. So that causes even more warming than what you might expect. And of course, as academics, we're very used to traveling a lot. It's an important part of disseminating our research, networking, and so on. And so it's interesting to know how much do we do this? What ways could we find of reducing demand for air travel? Because unfortunately, it's a very difficult area to decarbonize. So we might have access to commercially available electric planes sometime in the 2030s, but they're only going to be able to cover short distances. So it would be a lot easier for reaching climate mitigation targets if we could just reduce demand. One thing that has an effect on demand is what kind of tickets that you're booking. So some academics like to fly high, go in first class.
Not many. I mean, we all like to, but most of us can't.
Yeah, it's a good point. My research at UBC shows that a decent amount of emissions can be attributed to first class or business travel, and the reason for that is
faculty
because...
who fly? Hey, I want different grants, okay?
Yeah, so it's something interesting to look into, the policies that we have around that at UBC. Maybe this is a contentious topic.
I'm tired of the cargo class.
And so the last area that I'm interested in is politics. If you talk to people about making individual changes, one response that I have seen a lot is, look, it's not up to the individual, it's up to corporations, it's up to politicians to lead the way. And so you get things like, stop obsessing with how personally green you live and start collectively taking on corporate power. Or the number one recommendation is to overthrow capitalism. And those are, I guess I don't want to cast judgment on that one way or another, but political action is well and fine. We have a lot of research on consumer behaviors and what consumers can do, and we can make some good recommendations about how they go about it. We have less understanding of how you can most effectively engage politicians on the topic of climate change. So if you wanted to ask what messages work well when reaching out to the public about climate change, there's a wealth of research for that. What about if the public wants to reach out to politicians? How should they approach that? And so that's something that I hope to explore more fully. It's also the chapter of my thesis that I've gotten the least far on, so I don't have a lot of insight for you just yet. Simon?
Simon, do you fly business class?
So just to fill in to explain, since you're wondering, what Seth and I did through funding from the Pacific Institute of Climate Solutions was collect data ground up from departments around UBC. We asked the department's permission for that, although we didn't actually have to because the dean just said yes and pushed everything. And so that's how we have records on everyone's air travel. Of course, we cannot. It's all been randomized. There will be all assigned numbers, so we don't know who is who. But there is. You're not allowed to buy a business class, a non-economy class ticket at UBC unless you have approval of the dean. You can buy it, you can't get it reimbursed. But that doesn't mean it doesn't happen. So it does happen, but yeah, and of course this would be the ticket that was purchased. If somebody upgrades it, that's their own thing and it wouldn't necessarily come to our, so just so you know. So I just want to thank everyone in the group for their presentations. I hope this gave a bit of a window into what we've been doing. And as I mentioned, the work I've been doing over the years sort of ebbs and flows, and this is what you've seen is sort of pretty much in the center of it, and there are a few things on the outside. The other thing, and really my contribution and how I'm a part of the IOF, is through the Ocean Leaders Program. And if you've wondered about how it came to be, when the IOF was created, there were a few of us that were on a committee, the University cast a committee to sort of figure out the creation of the IOF. And I made the suggestion, I said, well, if we're creating a new program, we should apply for a CREATE grant from the university, which is an ANSERC funding program, to do graduate training and do something new. And everyone's like, that's a great idea, why don't you do that? And so that's how Ocean Leaders came to be, with Amanda's help and many others. And so the idea of the program is sort of helping graduate students, postdocs, et cetera, in learning about sort of translating research into action. And so the main things that the program provides, obviously, is graduate fellowships, so it provides some fellowship money. We have the course, Fish 507, Grand Challenges in Ocean Leadership, where people work on sort of community projects and sort of learn by doing a little bit that way. We also have a number of workshops they're ad hoc. They're not always going to be scheduled the same time every year. They're not going to be the same every year, but they'll mostly just be during the academic semesters. There's also the opportunity for funding for internships, and you don't need to be a fellow in the program for any of this. You can contact us for it. So information about that will be coming out. People get stuff through the ILF email list. And the main things I want you to know is that we have a number of things coming up in November. Anyone's welcome to attend. You probably received an email about it. We only ask that you register so we can keep track of how much we have enough space.
And
for
then you
each
show
one.
up if you register. but
And
you
show
don't
up if
have
you
problems
register, of
with that,
course.
yeah.
Yeah, but please show up if you register. So we have one on engaging with policymakers, and includes somebody from the Georgia Strait Alliance, somebody from the City of Vancouver, and somebody from the provincial government. We have a storytelling workshop, which is being led by someone locally that works with the Story Collider, which is an organization we held a story training with last year. We have another workshop on sort of risk analysis and decision making later in the month. And following from the storytelling workshop, 8 days later, we're holding a show. And it's called Tales from the Sea, and it's going to be held at the ANZA Club, which is at, I'm going to forget, is it Ontario and 8th, I think? Sort of near Main and Broadway. At 8 p.m. We did something like this last year, but it was with the Story Collider, the outside organization and podcast, and we had so much fun. But we can't afford to do that again, so we thought, let's do it ourselves without the cost of the Story Collider. And so we'll be having that on the 8th, and I highly encourage people to come. It'll be a lot of fun. And if you're interested in any of these, get in touch with me. I can help you get yourself signed up. Or Dominica, who is a coordinator of Ocean Leaders, and her office is just down the hall there. So, and that's everything. Thanks, everyone.